Hello and welcome to Lecture 6 for the graduate course ECE 254B, Parallel Processing. In this lecture, I'm going to finish part 2' of the textbook. Remember that part 2 in the current textbook has been divided into parts 2' and 2". And today I'm going to cover chapters 6b and 6c, therefore completing chapters 5 and 6 in the textbook. And beginning with lecture 7, I'm going to cover chapter 7 and then chapters 7a, 7b, and 7c to complete part 2 altogether. Now, chapters 6b and 6c deal with implementation issues for shared memory. In other words, we introduced and used for programming an abstract model of shared memory that we call PRAM, Parallel Random Access Machine. And now that we know how to program this abstract machine, we may wonder how this will be implemented in hardware. What are the challenges? And we will see that we have to make some compromises in order to make that model realizable in hardware. And those compromises basically affect the ease with which we can program the machine, and also the performance that we get from the machine. So these are basically topics discussed in chapter 6b and 6c. Ideally, we needed 2 lectures to cover these 2 chapters, but in order to fit the entire content of the book into a 10-week quarter, I've had to merge the coverage of some chapters. So the main challenge in implementing shared memory is to ease the memory access bottleneck. In other words, provide low latency, high bandwidth paths to memory, reduce the need for access to non-local memory, and reduce conflicts and sensitivity to memory latency. These will become clear as we discuss the various topics in this chapter. Okay. Now this new chapter 6b consists of section 6.6 in the original chapter 6, plus a whole lot of material from later chapter in the textbook that in this reorganized design of the book now fall in chapter 6b. So these are the various chapters 14, 15, 16, 17, 18, and 20, from which material has been moved forward to this chapter in order to put all aspects of shared memory in the same part of the revised textbook. Okay, remember that PRAM needs a read and write access to memory in every cycle. So PRAM is viewed as a synchronous machine, and in every machine cycle, a read access takes place, some processing takes place, and a write access. Now, even for a sequential computer, memory is already tens to hundreds of times slower than arithmetic logic operations on the processor. Therefore, memory is a bottleneck. Remember, we talked about the memory wall. Now, if multiple processors have to access a shared memory, this can only make things worse, because the memory now has to service multiple processors rather than just one processor. So shared access to a single memory, single large physical memory, isn't scalable. You may get away with it with a handful of processors. Even there, you have a challenge. because, as I said, memory is a bottleneck even for one processor. But you may expect to be able to manage if 4 processors, for example, access the same memory. So here are some strategies for making the PRAM model practical or memory scalable. First, make memory accesses faster and more efficient through methods such as pipelining. We'll see how this is done. Reduce the number of memory accesses by providing caching of data near the processor. Reordering accesses so that basically slower accesses do not impede the performance of processors that happen to get faster accesses. Reduce synchronization so that slow memory accesses for one computation do not slow down others. So this will be discussion of synchronization and memory consistency in Chapter 6C. Distribute the memory and data to make most accesses local. We'll see how this is done. And finally, store data structures to reduce access conflicts. An example of that is skewed storage that we'll see towards the end of this chapter, Chapter 6B. Okay, recall that shared memory looks like this in abstract terms. There are a bunch of processors, P of them in this diagram, and a bunch of memory modules or memory banks, M of them. And then the processors can access memory banks simultaneously, and the processor to memory network provides this capability for multiple processors to access multiple memory banks. In the simplest case, the processor to memory network is just a single bus, or perhaps a few buses. Now we can get away with this because the bus bandwidth is much larger than the memory bandwidth. So for example, if the bus cycle is 1 nanosecond, and the memory access time, let's say, is 100 nanoseconds, then 100 accesses can be performed through the same bus, or maybe 50 if 2 bus cycles are required for each access. 1 bus cycle to send over the address, and another bus cycle to receive the data. So anyway, dozens, perhaps hundreds of memory banks can be accessed through a single bus without the bus becoming a bottleneck, because the bus is much faster. More commonly, however, we have an actual network rather than a bus. And this network tends to be quite complex in terms of hardware. In fact, it is not uncommon for large parallel processors to have the bulk of their cost and energy consumption in this processor to memory network. So it's complex, it's expensive, and it may actually be a bottleneck despite the large amount of money invested in its design. It can still form a bottleneck, slowing down the processor. Notice that I/O channels are also connected to this network so that the processors can simultaneously access multiple parallel I/O channels. And I/O channels can transfer data into multiple memory modules simultaneously. Okay, conceptually, the simplest processor to memory network is a crossbar switch. And this is an example of a crossbar switch design. So here I've shown processor 1 is accessing memory module 3, and processor 4 is accessing memory module 5 through this crossbar switch. So these switches basically route straight through, and this one basically makes a turn, right turn. So basically, if processor 1 wants to access memory module 3, the crossbar switch at the intersection of this row and this column changes its state from straight through to bend or turn in order to accommodate that access. It's easy to see that this crossbar switch allows all the 8 processors to access different memory modules, provided they access different modules. Okay, so any permutation pattern is routable through such a crossbar switch, where a permutation means that processor 0, 1, 2, 3, 4, 5, 6 access some permutations of the memory modules. So for example, P0 accesses M7, P1 accesses M3, P2 accesses perhaps M1, and so on. So a permutation of these numbers 0 through 7 defines the memory access pattern. Now, even with this, so this crossbar switch has a cost and therefore energy consumption of order P squared. So if you have P processors, and typically we have the same number of memory modules, P memory modules, the number of switches in this crossbar is order P squared, and therefore its cost grows with the square of the size of our multiprocessors. So imagine if you have 1,000 processors and 1,000 memory modules, the cost will be 1 million switches. So it's not very scalable, and it's expensive, and as I mentioned, energy hungry. It uses a lot of energy. Now, even with the permutation network, the full PRAM functionality is not realized by this system. Remember, in PRAM, we said any processor can access any memory location. Here we say any processor can access any memory bank. Now, this memory bank M5 has many locations in it, many addresses. And if processor 4 is accessing some address in that bank, then the other processors cannot access other addresses in the same bank, okay? So we are restricting the functionality of PRAM in this implementation by saying the processors cannot access arbitrary set of memory addresses, but they can access an arbitrary permutation of memory banks. Fortunately, it's possible to store the data judiciously in these memory banks so that we never need, in the course of a computation, to have, say, 2 processors both access the same memory bank. Okay, we make sure that data is distributed among the memory banks so that the access patterns that we are interested in always lead to different processors accessing different memory banks. And we'll see examples of these shortly. Okay, we can also use a bus as the processor to memory network, either a single bus or multiple buses. A single bus, as I mentioned, if it has a high bandwidth, with a small number of processors and a small number of memory banks, it may not constitute a bottleneck. Going to multiple buses basically eases that bottleneck a little bit because different processors can access different memory banks through different buses. But then here we have the challenge of scheduling the buses. Here, every processor uses the same bus. Therefore, scheduling is not an issue. We need bus arbitration. So processors that want to access memory issue request to an arbiter, and the arbiter basically decides which processor is allowed to use the bus on any given cycle. So that's some kind of scheduling, but it's easy to do. Whereas here, because there are multiple buses, we have to decide which bus each processor should use in any given bus cycle. So it's a little bit more difficult to schedule. In either case, the scalability is poor. With a single bus, maybe we can go to dozens of processors of memory banks at most before bus loading becomes a problem and also bus bandwidth becomes a problem. Of course, if you have 3 buses, then you can do 3 times as many, but still, it's not very scalable. Okay, so if you have a single bus system, this is a sort of back of the envelope calculation to show you that performance will be limited by this single bus. So let's say we have a bus frequency of 0.5 gigahertz, meaning 2 nanosecond bus cycle. Let's say data width is 256 bits or 32 bytes. Typically, buses are wide in modern processors. We don't have 32-bit buses, but we have much wider buses. Let's say memory access takes 2 bus cycles, one to send the request and one to receive the data. Then the memory bandwidth with a single bus will be 8 gigabytes per second. Okay, 8 gigabytes per second is not very impressive for a large multiprocessor system because these are typically used in applications that are data intensive and a lot of data must be sent back and forth between memory and processors. Of course, if you use multiple bus systems, you can increase that by some factor, let's say 3, even though you may lose some of that increased bandwidth to overhead of scheduling and waiting, but in the best case, but still, you can improve that from 8 gigabytes per second with 3 buses to at most 24 gigabytes per second, which is still low for many parallel processing applications. We can use hierarchical bus systems. I showed this diagram to you before, where by using multiple buses, we try to do local communications in clusters of processors through separate independent buses, therefore increasing the bandwidth. And then when clusters need to communicate with each other, we use higher level buses. And our hope is that those higher level buses, which would constitute a bottleneck because, say, there's just one top level bus, are used rarely so that the bandwidth does not become an issue. Okay, the next idea is to use caches near the processors so that instead of the each processor having to go to memory through this network for every memory access, the hope is most of the memory accesses are satisfied from local caches. So if the cache hit rate, for example, is 95%, 95% of the accesses are satisfied locally, and this network and the memory modules are not involved. And in 5% of the cases, traffic is generated through the network and memory is accessed. So this basically, if it works, it allows us to use more processors without saturating the network or making it a bottleneck. Of course, using multiple caches creates the challenge of cache coherence. So if 2 processors share data so that 2 different copies of the same data appear in 2 different caches, then keeping those copies consistent requires some care, and it generates some overhead, some performance degradation to maintain that consistency. Okay, but assuming that we can solve that coherence problems, and we'll talk about some methods shortly, then this is a very good idea to reduce the traffic through the processor to memory network. Okay, so caching works, and this is something you should know from your computer architecture courses, because the effective access to the memory will equal to access to the fast memory to the cache plus 1 minus R. R is the hit rate. So if the hit rate R is 95%, only 5% of the time we have to access the slow memory, and basically 95% of the time we find the data in the fast store. So on every access we consult the fast store. That's why this appears here. And in this fraction of accesses, we also consult or access the slow store. And if this fraction 1 minus R is very small, then this slow access time is multiplied by that small number and therefore does not have a large effect on the effective access time. And here I've shown a two-way set associative cache. If you don't know about various architectures for caches, direct mapping, fully associative, and set associative, please make sure to review a computer architecture textbook of your choice, including my own computer architecture textbook. You can find a discussion of cache memory in various ways of organizing. So benefits of caching, see here's an analogy. When you're sitting at your desk, some documents that you're accessing frequently are on your desktop. Other documents that you need them, but not as often as these, may be in drawers here, close by. And other documents may be in the file cabinet. So this is sort of level 1 cache, level 2 cache, and main memory. So most of the times you're accessing documents that are on your desk because you have already fetched them and put them there to work on. A small fraction of cases you may need to go get new documents from your drawer. And an even smaller number of cases you need to go to the file cabinet and fetch things that you have filed away. And this effective access time that I showed you on the previous slide leads to a speed up, which is the slow memory access time divided by the effective access time. And this speed up can be written, this is just algebraic manipulation, in a way that resembles Amdahl's law. Okay, why is this Amdahl's law? Because the speed up is 1 over the fraction of accesses whose speed does not change. That's basically the missed accesses. Plus this is C slow divided by C fast is basically the speed up. The speed up that the cache offers over the slow memory. Okay, so in this case, speed up occurs. In this case, there's no speed up. So this resembles Amdahl's law in terms of if this fraction 1 minus R, let's say, is 10%, 10% miss, then the speed up cannot exceed 10. 1 divided by 0.1 is 10. The same way that Amdahl's law was used. And this is a generalized form of Amdahl's law. I'll leave it up to you to study. Okay, one of the ways that we connect processors to memory modules is through multi-stage interconnection networks. And I'm going to show you an example of a multi-stage interconnection network first before discussing them in greater generality. So one specific example. And that specific example comes from the Cray YMP computer. This is an old computer, but the interconnection network is still interesting and worth discussing. So this is a vector machine that has a bunch of vector registers, 64 entries. So if you have a vector of 64 elements, you can put that vector in one of these registers. If you have vectors that are longer, then you can bring chunks of that vector. So if you have 256 element vectors, you can bring a quarter of that vector in, operate on it, and then bring another quarter and so on. Or use another register. Okay, so you have 8 registers, V0 through V7, that you can use at will to store vectors or chunks of vectors. And then the machine basically can operate on vectors. So you can add 2 vectors that are in V0 and V1 and perhaps store the result in V2. So this machine basically has vector operations, and these vector operations are performed through pipelined arithmetic units. So elements of a vector are sent to this pipeline, one per clock cycle, even though it takes multiple clock cycles to multiply in the pipeline. Every clock cycle, one new element of the vector can be sent to this multiply pipeline. And then from the other end, the result of multiplication goes back to this vector. So this is basically called pipelining. You can also do pipeline chaining. So for example, you do multiply, add. So you send values to the multiply unit. The values are forwarded to the add unit, and then eventually find their way back to a result register. Now, the reason I had to describe this part of the architecture, only this part, is that this particular machine, the processor has multiple access channel to memory. And the typical usage is that we are doing 2 vector reads from memory. So we are basically loading 2 vectors into these registers through these 2 channels. And perhaps storing a vector that resulted from a previous computation into memory. So there's pipelining in memory accesses too. So for example, as I'm operating on V0 and V1 and storing the result in V2, I'm preloading V3 and V4 for some subsequent vector operations, and I may be storing V5, which was the result of a yet previous operation, into memory. Okay, so there are 2 read channels, 1 write channel or read-write channel, and there's also another channel for the sequential part, instruction fetching and other. Those are not of interest to us here. Okay, so we fetch vectors into registers. We do operations through these pipeline units, find vector results, and then store vector results into memory. And this is basically the network that allows each processor to access memory through its 4 access channels. So each processor has 4 access channels, and these are the switches that connect the processors and their access channels to 256 memory banks, numbered from 0 to 255. The reason we have so many memory banks is that we want to be able to do concurrent access as much as possible. Okay. So processor 0's 4 channels, this is a 4x4 crossbar switch, can be directed, each of these can be directed to this switch, to this switch, to this switch, to this switch, and therefore we want each processor to be able to access all the memory banks. And then this is an 8x8 crossbar, which allows each of these input channels that can come from these 4x4 switches to be directed, to be connected to these 1x8 switches. And then on the other side of these 1x8 switches are 8 memory banks. And the 8 memory banks up here are numbered 0, 4, 8, 12, up to 28, and so on. The ones here are numbered 32, 36. So if you access memory banks 0, 1, 2, 3, you can access them simultaneously because the path to them goes through different switches in this network. Okay, so this numbering is designed to allow simultaneous accesses to consecutive memory banks, consecutively numbered memory banks. Okay, so why they decided to implement this in this way is not clear to us at this point. There's a lot of theory behind design of interconnection networks. And of course, the optimal design depends on the expected access patterns. So designers of this particular machine decided that this was a good way to go. There are many, many other so this is a multi-stage interconnection network because processor requests to memory go through three stages of switches. Stage 1, stage 2, stage 3. Okay, one of the better known multi-stage interconnection networks is the butterfly network. We will revisit butterfly again and when we talk about the circuit model of parallel processing in part 2 double prime. In fact, the first time this network was discovered, so to speak, was in connection with fast Fourier transform algorithm. But for now, let's just take it as a design. So there are basically 2x2 switches. So here you see two processors are connected to the switch and there are two outgoing channels. This switch is also 2x2 and so on. On the other end, this switch is 2x2 and it's connected to two memory modules. This is one way in which we can use this 8-row butterfly network for connecting 16 processors to 16 memory modules. We can also, there's another version of this, where these switches in the first column, instead of being 2x2 switches, are 1x2. In other words, this switch is connected to just one processor on this side, but there are two outgoing channels. And this switch is also connected to one memory bank, but it has two input channels. So edge switches are 1x2 and 2x1, and that would connect 8 processors to 8 memory modules. There are reasons we might want to do that, even though it would accommodate fewer processors and fewer memory modules, because the routing, the possibility of conflict in routing is reduced when you use fewer processors and fewer memory modules. Okay. So butterfly is basically a multi-stage interconnection network. And this is actually called binary butterfly because it uses 2x2 switches. We can also design emery butterfly networks, which use M by M switches. Okay, but the theory is basically the same for either binary or emery. We focus on binary because it's simpler to discuss and understand. Okay, on the butterfly network, one of the nice properties of the butterfly network is that routing of messages between processors. So here I've shown basically the case where the switches on the edges are 1x2 and 2x1. So there are 8 processor modules on this side and 8 memory modules on this side. Sometimes we consider what we call wrapped butterfly. A wrapped butterfly is when you take this butterfly that is spread out, sort of turn it into a cylinder, so that these rightmost nodes are superimposed on the leftmost node. Okay, so you wrap it around. And in that case, this becomes a processor-to-processor interconnection network. Okay, so it connects one processor here to other processors rather than being a processor-to-memory interconnection network. Okay, so what is the notion of self-routing? Self-routing refers to the fact that when you want to route, let's say, from processor 3 to memory bank 6, the path, you don't need to figure out what path. That path is automatically deduced by the message itself as it finds its way through the network. And that's a good property because you don't need to pre-compute a path. How is that? Okay, let's take the example, send from 3 to 6. 3 in binary is 0, 1, 1. 6 in binary is 1, 1, 0. If you XOR these together, you get 1, 0, 1, which is called the routing tag. And the message carries with it this routing tag. And this routing tag, when read backwards from end to the beginning, basically dictates the setting of the switches. 1 means the switch is set to the cross state. 0 means it's set to straight state. So this one, basically, this routing tag says cross, straight, cross. So here it is, cross, straight, cross. Another example from 3 to 5, 0, 1, 1 XOR with 1, 0, 1, which is 5, is 1, 1, 0, and this one will be straight, cross, cross. Straight, cross, cross takes us from 3 to 5. And one final example from 6 to 1, 1, 1, 0 XOR with 0, 0, 1 is 1, 1, 1. So the route from node 6 to processor 6 to memory bank 1 is cross, cross, cross. And here it is, you see it, cross, cross, cross. Okay, therefore we don't need to worry about finding a path. The path is basically predetermined. That's an advantage, but there's also a disadvantage, because if anything, any part along this path is broken, either the links or the nodes, the switches, then that path does not exist because there's no other path from processor 3 to memory module 6. Okay, we'll talk about more robust networks later on, but this is both an advantage in terms of simplicity of routing and a disadvantage in terms of lack of robustness. A butterfly network is not a permutation network. There are many permutations basically that can be routed, as shown in this example. Processor A or packet A goes from processor 1 to memory module 0. B goes, you see these 4 paths are established without conflict, and therefore these 4 accesses can be performed simultaneously without any conflict, because the request and then the results go through independent path, node disjoint and edge disjoint paths. On the other hand, if processor 0 wants to access memory bank 4, processor 1 wants to access memory bank 0, these 2 paths will share this link and will share these 2 switches, and therefore they cannot both go through simultaneously. There's a conflict, and the worst case conflict can be pretty bad in butterfly network. So our hope is that most of the times we encounter situations like this, or very few conflicts. In this case, one of the requests must be delayed. So for example, this one is sent through this link, and then 1 clock cycle later, perhaps this one can go through, so that they go through this edge and through these switches in different clock cycles. So if there are minimum conflicts, a small number of conflicts, then the situation won't be that bad. Okay, I'm going to skip this slide in the interest of being able to cover all the material that I have. There is this network called Benesch network. Benesch is the basically name of the person who invented this, or basically thought about it. It's two butterfly networks back to back. So here's a 4-row butterfly network. Oh, by the way, I shouldn't have skipped the previous slide. This one. The structure of the butterfly is that nodes 0 and 1 are connected in the between 0th stage and first stage. So this is the +1, this is the -1 connection. So 0 to 1, 1 to 0. In the next stage, we have +2 and -2 connections. And in the last stage, +4 and -4 connections. Okay, so this is how we can get from any node to any other node. So basically, this allows us to, this is why, this binary node ID is relevant. This allows us movement by 1 step. This allows us movement by 2 steps in terms of the rows that we visit. And this allows us movement by 4 steps. Okay, back now to where we were. So this is a butterfly network, ±1, ±2. This is the end. This is a reverse butterfly, ±1, ±2, and then they share these nodes. So a forward butterfly, a reverse butterfly that share this column is known as a Benesch network. The nice thing about Benesch network is that it is indeed a permutation network. So it uses more hardware than a corresponding 4-row butterfly, almost twice as much, because it's 2 copies of a butterfly. But it allows any 2 to the q. So a 2 to the q row Benesch network allows any 2 to the q by 2 to the q permutation. Here's an example that you see some paths are established between various processors and various memory modules on the other side. Now, if I suddenly decide that I want to, in addition to those connections, I want to also connect, let's say, processor 10 here to memory module 10, let's say, which is not used here. Memory module 11, memory bank 11 is used, but 10 is not. So let's see if I can connect 10 to 10 through this Benesch network. Okay, well, I can't go straight through because this link is already being used and this link is being used. So I might try to use, so I can't go to here. Maybe I can go to here because then I can deflect. So I have to try various paths. And even though this is a permutation network, I may not be successful in establishing this new path. The reason is that when I say this is a permutation network, if you give me a permutation, I can route it through that. But if I add something to already existing connections, there is no guarantee that I can route that extra additional path while keeping the other paths intact. So sometimes this is called a rearrangeable network. In other words, I may have to rearrange the other paths that are already there in order to be able to establish this new connection. But if I want to connect 10 to 10 and also maintain all the other ones, there is a way to do it. But those other paths may change in the process. Okay, augmented data manipulator network is a name for a network that is basically a super graph of the butterfly network. If you look here, all the connections of butterfly network, like 0 connected to 1, 1 to 0, 0 connected to 2, 2 to 0, and so on. All the butterfly connections are there, but there are other connections that did not exist in the butterfly. Oops. For example, in butterfly, 1 was not connected to 2, and 2 was not connected. Okay, so this is called plus or minus 2 to the I network. That's another name for it, because every node, 0 is connected to 1, 1 is connected to 2, 2 is connected to 3. So this is plus 1, then minus 1, plus 2, minus 2. Whereas in the butterfly network, the plus 1 connection existed, but only for even numbered nodes. To make sure we understand this, let me go back. Okay, so the plus 1 connection exists for node 0, but not for node 1. Doesn't exist. Okay, so this is makes this augmented data manipulator network more flexible than butterfly, because there are occasionally multiple paths. So in order to go from 2 to 4, input 2 to output 4, notice I've highlighted 2 different paths. So this makes it more flexible. If this path is congested because other messages, other accesses are going through this switch, for example, I can use that alternate path. Okay, tree networks can also be used as multi-stage interconnection networks. So imagine that these, so this is a tree. Imagine that these boxes are switches, and I connect processors to these leaves. Then any processor can access any other processor, or any process. Let's say I can also connect maybe processors here and memory modules here. But the thing is, the paths from one side of the tree to the other side of the tree always go through the root and through these two links. So if there are a lot of connections to be made through the root of the tree, the root and these links leading to the root can become bottlenecks. So this led many years ago to the proposal for what are known as fat trees. In fat trees, communication channels between nodes become wider or faster, greater bandwidth as we go up the tree, so that if multiple accesses go up the tree from these processors, then those multiple accesses can be routed through these wider channels or faster channels, and therefore the bottleneck disappears. Okay, well, a disadvantage of this is that the nodes are no longer, the switches are no longer uniform, identical, because the switches, say, in this level have different bandwidths on their inputs and outputs compared with switches in this level. And furthermore, there is a maximum bandwidth that we can achieve on a single channel, and we can't go beyond that. Okay? So this led to the idea of, instead of one wider or faster channel, let's use multiple channels. Okay, this removes one of the objections. Now, each of these channels can be of the same bandwidth of each of these channels. So there are 4 channels coming in and 4 channels going out, so the bandwidth will be the same. However, again, the design of these switches is different. So here I have a 2x2 switch, 2 inputs, 2 outputs, and here I have a 4x4 switch. Okay, so it's less desirable. So jokingly, some people say, instead of calling this a tree and these fat trees, we should call these trees, because basically this is the way trees in nature look like. You know, the branches that are closer to the root are thicker, tend to be thicker. And then we should call this a skinny tree, because it's not like a regular tree that we see in nature. Okay, So in order to remove this objection that now these switches are different, we can do the following. So because this switch has twice as many input channels and twice as many output channels compared to these switches, we basically provide multiple nodes. So this one node is decomposed into two nodes. This one node is decomposed into 4, and the root node into 8. And then these two have two parents, 0 and 1. Each of these has two parents. Okay, it's hard to see what ones the parents are, but there are two parents. So an access request that comes here always finds a way to go there, and each of these nodes is no more complex than the nodes all the way at the bottom. Okay, so this is basically a practical implementation of a fat tree using nodes that are all 2x2 switches. Well, interestingly, this network that you see in this diagram is nothing but the butterfly network, except it is drawn differently. Imagine these 8 nodes. Just turn this diagram so that these 8 nodes go to the left edge. These 8 nodes go to the right edge, and this becomes exactly the butterfly network. So another way to view the butterfly network is basically to consider it a practical implementation of a fat tree network. There are many interconnection networks, and we really don't have time to study all of them. So much so that in this diagram you see the C of indirect interconnection network. These are just some of the examples that you can find in the literature. There are many more multi-stage interconnection networks, indirect interconnection networks. Okay, you can also design, I mentioned that butterfly network is self-routing, but it's not a permutation network. We can, in fact, design permutation networks that are self-routing. And the design of self-routing permutation networks is related to the design of sorting networks. So here I've shown processors 0 through 8 wanting to access memory banks as shown here. So processor 0 wants to access memory bank 7. Processor 1, memory bank 0, and so on. Basically, if I sort these numbers as they go through this network, then access to the corresponding memory bank is provided, because in sorting, 0 will go to the top. Okay, 1 goes into the next element. And this is a sorting network. Okay, that is basically uses what we call classifiers. So a classifier basically takes these 8 inputs, puts the smallest 4 on the top outputs, and the largest at the bottom, in no particular order. Okay, so 0, 1, 2, 3 are the 4 smallest, they go to the top. 4, 5, 6, 7 are the largest, they go. So this is a classifier network that classifies the inputs into 2 categories, the small ones and the large ones. And then I use 4 input classifiers in the next stage. 0 and 1 end up at the top, 2 and 3 at the bottom, and so on. And then 2 input classifiers. So this is a sorting network built of classifier networks. And it can route any permutation. So you give me this permutation, I just input it into this network, and by sorting these values, I can provide the appropriate connection, connect this one to memory bank 0, this one to memory bank 1, and so on. We talk about sorting network when we get to the circuit model. And this is just for your reference. I won't go through it. Some of the names of multi-stage interconnection networks and properties of these networks that you may find in the literature. So this is a good point for reference if you encounter, for example, the name bi-delta network. You can come here and there's a brief definition of what it is. Okay, I mentioned that we need cache coherence protocols if we use caches for the process for multiple processors. And here I've shown the types of problems that we need to resolve. So this is memory. These are caches, and these are the processors. So each cache is private, and I've only shown 2 locations in the cache for simplicity. Here is data element W in main memory, and there are 2 copies of it in these 2 caches, and those copies are consistent. In other words, they have the same value. And this leads to no problems. Each of these 2 processors can access W at high speed and the 2 are consistent, so for reading they both get the same value. However, if one of them decides to write something into this and turn W into W prime, then the 2 copies become inconsistent, and we have to deal with that. Okay, X has a single copy, and therefore, obviously, if you have a single copy, it's consistent, and then if this processor decides to write into this copy becomes inconsistent with the copy in memory. But as long as the other processors do not access X in memory, this inconsistency is not a problem. Eventually, this processor will write this new value, updated value there, and the main memory becomes updated, and therefore there's no problem. So as long as you have a single copy of a data item in cache, and only this processor accesses that copy, there's no problem in changing that. So read-write access is allowed. Y has 2 copies. I'm sorry. Y has 1 copy, but the copy is inconsistent with the copy in memory. And Z has 2 copies. And these 2 copies, one of them is inconsistent with memory, the other one is consistent. In other words, this one perhaps updated Z to Z prime and also wrote it back to memory, but this one is an invalid or stale copy. This is very dangerous because if this processor uses this data, it gets a stale copy, an invalid copy, and the computation will not be correct. So we have to avoid this situation. So how do we avoid that? We have cache coherence protocol. And these are these protocols you should have seen in your computer architecture course, whether you took it at UCSB or elsewhere. This is a standard discussion in computer architecture. So I very briefly describe these. Please refer to a computer architecture textbook if you have trouble understanding these, including my own computer architecture textbook describes. So this is the Snoopy protocol. The assumption is that all the processors are connected to a bus. So the processor to memory network is a bus. And therefore, whenever a processor communicates with memory, all the other processors can see that communication by snooping on the bus. So because they're connected to the bus, they see all transactions on the bus, and therefore they become aware. So if one processor, for example, fetches something from memory or writes something in memory, all the other processors will know about this or can potentially know about it by monitoring the bus. Okay, cache lines this protocol in one of three states: exclusive, read-write; shared, which is read-only; and invalid. So for example, if two caches have shared copies of a data, they can read that data as much as they want. But if they want to change that data, if a processor that has a shared copy wants to write into that data, okay, so if the processor wants to write, whether it hits or misses in the cache, it puts a write miss on the bus. It basically informs the other processors that I want to write into this. Okay, and then the status of that line becomes exclusive, meaning that all the other copies of this cache line will be invalidated by the other processors. And this processor that wants to write into it assumes exclusive ownership of that block and then can modify it. Okay, so each of these transitions basically has two parts: the label. One is what happens on the bus, what is observed on the bus, and then the action taken as a result of that observation. So a shared copy may become exclusive. A shared copy or an exclusive copy may become invalid as a result of some events that are observed on the bus. So this is as much as I want to talk about this. Implementing a Snoopy protocol is not that hard. And this is one possible implementation. So the cache memory, which typically has a tag store, where whenever the CPU wants to access data in cache, it looks at the tag to see if this line contains valid data that the CPU is looking for. If there's valid data, it fetches it. If it's not valid data, let's say this is direct mapped for simplicity. So there's a particular location that it needs to look to find the data. If that location does not contain that data, but contains something else, the tag is different, then that data must be kicked out of the cache. It's put in a buffer to be written back into memory, and then the address is sent to memory so that the data is fetched and placed there, and the CPU can now access it. So that's the standard operation of the cache and the way CPU accesses the cache using the tag store. There is a second tag store here that is used for snooping or monitoring the bus. And whenever a transaction on the bus occurs and there's an address, we check to see if that address is inside this cache. And if that address, in other words, if this cache owns a copy or contains a copy of that data that is subject of that transaction on the bus, remember that, processors are monitoring the bus, and when they see something on the bus, they check to see if they hold a copy. If they don't hold a copy of that data, then that transaction is not relevant to this particular cache. If they do hold a copy of that data, depending on the status, whether it's exclusive, shared, they have to take appropriate action, perhaps to invalidate it or turn it from exclusive into shared, or turn it from shared into invalid, and so on. Okay, and when this comparison of the address of the bus with the tags takes place, also the tag of this buffer, remember that something that was kicked out of the cache goes into this buffer and is not yet written into memory. So the tag of that one is also compared in case we have to invalidate or change the status of this thing that is no longer in the cache, but it's still not in main memory. Okay, so this is a simple implementation of the snooping cache coherence protocol. Now, this snooping protocol is not scalable because you cannot connect too many processors to a single bus. So in distributed memory, shared memory processors, you have different memory banks, each associated with a processor. And if a processor wants to access this memory bank, it has to go through the interconnection network and through this other processor in order to access its data. So access to remote locations are slower than access to local locations. Now, in this case, if processors share data, so copies of the same data are in two different caches, we need a coherence protocol, and that's known as directory-based protocol. Now, typically, when data is shared between processors, it's shared among a small number of processors. In other words, it's very rare to have, all or almost all processors sharing data. So the way a directory-based protocol is implemented, we have a directory that indicates to us where the shared copy of a particular piece of data are located. Okay, that's called the sharing set. By the way, this is a correction to the diagram in the textbook. Please make that correction. This is figure 18.4. So the sharing set, whenever a new cache decides to access a particular piece of data, then that cache is added to the sharing set. So the sharing set grows by this new cache. So we now have another cache in the sharing set. And then again, the data has three possible states: exclusive, read-write, shared, read-only, and uncached. And uncached data is in main memory, but has no copies in any of the caches. So if there's a read miss by any processor, the memory is accessed, and this uncached piece of data is returned, but the sharing set now becomes C. In other words, there's one cache now that shares that data, and data becomes read-only. Okay, it's shared. Okay, similarly, again here, each transition is marked with the event that occurs, say read miss, followed by a colon, followed by the actions that are taken in response to that. So there are two ways of implementing this directory, two main ways. There are other ways too. One is a bit vector. So for each piece of data, there's a bit vector that says which caches contain that piece of data. This is a pretty simple way, as long as the number of caches is not too large. The number of processors is not too large. So if we have 32 processors, maybe 64 processors, then this bit vector approach may be reasonable. If you have many more processors, then this bit vector approach is wasteful. And you can use a scheme shown here. So here, this is memory, and these are 4 processor caches. So this particular block of data is in main memory. There are also copies of it in cache 0, cache 0, cache 2, and cache 3. And these copies are linked together so that when something happens to this piece of data and we have to invalidate or change the status in those caches, we know where they are. So you follow this link to get to this copy of data, you follow that link to get the second copy, and follow this link to get this third copy. Okay. Similarly, if this cache decides to do something with this data, it knows how to notify all the other caches about that change. So this is more scalable as long as the number of caches sharing any particular piece of data is not too large. This is scalable. It can have even millions of processors, and this will be quite efficient if, say, you expect 8 caches to share a particular piece of data. Okay, section 4 in this chapter deals with data allocation for conflict-free access. So these methods are described in terms of matrix accesses because those are more easily understood. So suppose I have a 6 by 6 matrix. Again, typically matrices we deal with in parallel processing are much larger, but let's take a small example. And in matrix algorithms, we are interested in accessing rows of matrices and columns of matrices. For example, in matrix multiplication, okay? So if I store this particular matrix so that its column 0 is in memory module or memory bank 0, column 1 is in memory bank 1, and so on, anytime I want to access a row of these matrices, the elements that I have to access are located in different banks, and therefore I can access them concurrently. So let's say 6 processors can access those 6 different elements simultaneously because they reside in different memory banks. However, if I happen to need this column of this matrix, well, tough luck. All those columns elements of that column are in the same memory bank, and therefore I have to fetch them one at a time, and therefore concurrent access is not possible. Okay? So this gives rise to this idea of skewed storage format, in which the matrix is not stored in its natural format shown there, columns in the same memory bank, but in skewed format. So row 0 is stored beginning with this bank. Row 1 is stored beginning with this bank, and then it wraps around and goes here. Row 2 is stored beginning with this bank, and then it goes and wraps around, and so on. Given that this is follows a simple rule, it's easy to keep track of where to find each element. So elements of row 0, column J, are in memory bank J. Row 1 are in memory bank J plus 1, modulo 6. Okay. Now, a row of the matrix becomes accessible as before, concurrently, but also a column of the matrix. So this is column 2 of the matrix, the green elements highlighted in green form column 2 of the matrix, and they all happen to fall in different memory banks. Okay, in order to discuss methods for this, we generalize slightly. We say, okay, if we have a matrix, we don't view it as a 2-dimensional data structure, but as a 1-dimensional vector. So instead of saying row 0, column 0, which say element 0, row 1, column 0, element 1, row 0, column 1 is element 6. So we basically flatten the data structure into a vector. Okay, then when we want to access a column of this matrix, we are basically accessing consecutive elements, 0 through 5, 6 through 11, 12 through 17. So a column access basically accesses consecutive elements, we say the stride for this access is 1. Stride is basically the difference between one address and the next. If we want to access the row, let's say row 0 is 0, 6, 12, more generally k plus m, k plus 2m, so the stride becomes m, or 6 in this example, 0, 6, 12, 18, 4, 10, 16, 22. In some matrix algorithm, we are also interested in accessing the diagonal elements. In this case, the stride is m plus 1, or 7, 0, 7, 14, 21, 28, 35. And anti-diagonal elements, the stride is m minus 1, 5, 10, 15, 20. Okay, so if I'm interested in accessing rows, columns, diagonal elements, and anti-diagonal elements of this matrix concurrently, then I have to store the matrix elements in memory so that all of these 4 strides that I'm interested in fall into accesses with these strides fall into different memory banks. Okay? Now, if the number of memory banks B is a prime number, then this is ensured, because 1 is relatively prime. Let's say the number of memory banks is 7. 1 is prime relative to 7. Any number m is prime relative to 7. Of course, if m is not 7. However, using a prime number of memory banks is often inconvenient. In architecture, most things we try to make powers of 2. So 8 memory banks, 16, 32. In the Cray example, we had 256 memory banks, because that makes the address mapping easy. Okay, so using a prime number of memory banks is not an option. So we contemplate using an address mapping that is a linear function of I. So element I of the vector goes into memory bank A plus BI. A and B are constants, modulo B. Okay? With this is called the linear skewing scheme. In other words, address I is mapped into the location A plus BI modulo B. We do modulo B because we want to convert everything to 0 to B minus 1, which is bank number. Okay? This is called the linear skewing scheme. A linear skewing scheme, vector elements k, k plus s, k plus 2s, so this is stride s, will be assigned to different memory banks if and only if s times b is this constant that we used, is relatively prime with respect to the number b of memory banks. So of course, if we make b a prime number, then this is guaranteed. The 2 are guaranteed to be prime, but there are also other values of b that can be relatively prime to this one. Okay, so there's a theory with this. I just wanted to introduce you to basically an introduction to this theory of skewing scheme, linear. Now, the reason we are interested in linear skewing scheme, because then the address computation is not too difficult. If we want to see which memory bank contains a particular element of interest, then we basically perform a multiply-add operation. In fact, A can be 0 so that we don't have an add. And this B times I is a constant multiplied by I. There are simple algorithms. You don't actually need to do a multiplication to multiply a constant by an arbitrary number. That's why we're interested in linear skewing scheme. Okay, distributed shared memory we already introduced, where memories are basically behind the processors. So here's an example of a distributed shared memory parallel computer using a butterfly network as the interconnection network. I've only shown 4 of the processor memory pairs here. Each of these other rows also has processor memory pairs. So basically, this interconnection network that connects processor memory pairs together, in this example, is a butterfly network. And a processor wanting to access the memory in some other processor associated with some other processor has to route its request through this network until it gets there, and then the result flows back through the butterfly network. So that's one example. You can use any kind of interconnection network here. Okay, now I'm going to skip the next few slides, PRAM emulation with butterfly min, because we have more important things to discuss. Okay, one method for memory latency hiding is pipelining accesses through this interconnection network. Remember that memory accesses typically takes a long time, possibly hundreds of times more than operations. So if you're thinking in terms of PRAM, where a memory access takes place, so that's basically data flowing in this direction to the memory, result flowing back, and then a single computation step performed, and then the result being sent back to memory, the memory latency will kill this application. It's just too long. Now, fortunately, we can pipeline memory accesses. And here I've shown processor zero's access requests, these green boxes. So processor 0 sent this request, then this request, then this request to different memory modules, and they're flowing through the network because they're going to different modules that are at different places in the network. And then eventually the results start flowing back, and these orange boxes are the results. So at any given time, processor 0 has many outstanding requests that are going towards the memory or are coming back. Okay? Of course, it cannot perform a computation that depends on the result of this access until the result of that access comes back. But if this processor wants to fetch a vector and then perform a computation of that vector, it can send access requests for elements of that vector, and then the result will flow back. On every clock cycle, a new access request can be sent, and after an initial latency, which is basically the pipeline delay going forward and going back, it will start receiving replies to those requests, and therefore this hides the memory latency to some extent, because as far as the processor is concerned, every clock cycle is issuing a memory request, and after a certain delay, every clock cycle it's receiving the result of one memory request. Okay, so if the processor can access a whole bunch of data so that this pipeline latency is negligible compared to the total number of data elements accessed, then every clock cycle effectively one data access takes place. Okay, so let's now go to chapter 6C and discuss some ideas in this chapter briefly. I don't have enough time to go through all of the ideas. So this is basically a repetition of the previous diagram. Now, if these memory accesses imagine that different processors are issuing memory accesses. So it's entirely possible that some of the accesses of processor 0 will conflict with other accesses, whereas the other accesses do not. So this access, for example, here, may encounter a conflict and be delayed as a result, whereas this access is going through and it may overtake this access so that the result will come back out of order, okay? So we have to be aware of this and sort of develop a program so that either they're insensitive to that out of order delivery of requested results, or basically each of these accesses carries a timestamp with it, and if they arrive out of order, we know that they are out of order and act appropriately. Okay, one of the ways of, so I mentioned that some memory accesses may be delayed, and in fact the delay can also occur because multiple processors can access the same memory bank. So an access from this processor goes to this memory bank, some other processor, and they say arrive there at the same time. And then the memory bank can service only one of those. And the other one must wait for a long time until this memory bank becomes free. So even if they arrive on consecutive clock cycles, so this one arrives clock cycle I, the one from this processor arrives in clock cycle I plus 1, well, the difference between cycle I and I plus 1 is not enough for the first access to have been completed, and therefore the second one must wait. Okay, so if we can ensure in order delivery, then life becomes much easier. The semantics of the programs will be much easier, and they will work correctly as long as the accesses are always delivered to the processor in order. This requires that the processors be synchronized. So in order to avoid that, basically in order to synchronize the processors, the slowest access dictates how long it takes to access memory, the slowest request, okay? In order to avoid that, we don't synchronize the processors completely, but once in a while when needed. So here I've shown 4 processors running their own programs independently, so there's no synchronization between them. But at some point, because the result of, say, this processor now depends on the outcome there, we have to synchronize them to make sure that this particular piece of program is not executed before that one is completed. So this is known as barrier synchronization. Barrier synchronization means that all the processors must wait until they all arrive at this barrier before they are allowed to proceed. And this synchronization has some overhead. So in addition to the slowest processor dictating, how long each of these phases takes, there's also some overhead. And therefore, if we didn't have any synchronization, then these pieces of programs would run in this much time and would be done, just one synchronization at the very end. Whereas here we have multiple synchronizations, so it takes longer. So we want to minimize these synchronizations in order to avoid the overhead and inefficiency due to them. Okay, synchronization can also occur through message passing. So here I've shown 2 processes, A and B. B is dependent on process A because in message passing terminology, the process A sends a value X, a message X, and this one receives it. In other words, for process B to continue beyond this point, it must have received the value X because it uses it in its computations here. So these two are running asynchronously, except that when process B gets to receive X, and X has not yet been transmitted, it waits. And once X has been received, it's allowed to proceed. So X is sent here. This is basically the message transmission latency. It takes a while to get here. So process B waits. So sending and receiving of messages implicitly synchronizes processes. And this synchronization is more fine-grained than the type that we saw in describing, this task graph before. And I said, task 1 must complete before task 2 is executed. Task 2 must complete before task 3 is executed. So here we assume basically a worst case dependency, that 3 depends on the last thing that this 2, process 2, or task 2 completes. So it has to wait until that one has completed altogether before this one proceeds. Here, B is dependent on A, but it doesn't have to wait until A is completed before it does its job. It does part of its job even before, can do it even before A starts. Then it has to wait for only this part of process A to complete until it receives X, and then the rest of A is irrelevant as far as process B is concerned. So this is sort of a more refined types of only where values are needed by one process from another process does waiting occur. A process that needs something from another process does not have to wait until the other one is complete. Okay, so I'm going to skip synchronization with shared memory. Please do read this, and if you have any questions, ask me. They should be self-explanatory, and you should be able to understand it from the description here. And the next topic that I'll discuss, only briefly, is the notion of strict and sequential consistency. And this relates to the notion of time in distributed systems. Okay, from physics, you may remember that time is not an absolute thing, it's a relative thing. In other words, we learn in physics that two observers do not see the same time, because observing events at a different location requires information from that location to get to us, and that information cannot get to us faster than the speed of light. So if this is the current point, the present point, horizontal axis is space, vertical axis is time. So let's say a time is measured in years and distance in light years. So these 45-degree lines basically say the part of space in future that is observable to us, and the part of space in the past that is observable to us. Everything outside is not. Okay? Furthermore, speed of time passing varies with different observers. And this is basically from the theory of relativity. So the conclusion is that a universal notion of time does not exist in physics. In practice, the differences are small enough so that when we say, for example, to a group of people, somebody orders, set all your watches at 1 p.m. so that from this point on, we have synchronized time. We have the same time. Okay? Well, even though the people, depending on their distance from the speaker, will hear this command at different times, and assuming that the setting of watches is instantaneous, they would still not have exactly the same time, but the difference is so small that for all practical purposes, we can consider that as synchronized clocks. Now, in distributed systems, we run into a similar problem, and that is, so let's say three processes are running on three different processors, and each one writes and reads from different locations in a shared memory. So write into location 1, read location 2, write into location 2, write into location 3, and so on. So they're doing various things. The yellow process, the green process, and the blue process. Okay, of course, if you write into location 1 and then subsequently you read into location 1 later, you will be getting that updated location. You expect to be getting that updated value. In other words, this read should not give you the value that existed in location 1 before this write. That's pretty easy to guarantee within the same processor. Now consider what happens between processors. So this one writes into location 1, this one reads from location 1. Now in this timeline, I've shown this occurring after that. However, because it's impossible to synchronize clocks, the clocks running on these two processors can be approximately synchronized, but never exactly synchronized. There is a danger that this one will read a value that existed before here. There are delays, in writes taking place and reads taking place and so on. So basically, if we have events in different processes, we cannot guarantee. All we can guarantee is within the same process, the order of reads and writes must be honored. But between processes, we cannot guarantee that, especially when events are nearly simultaneous. Okay, so this one reads location 3, this one writes into location 3, and these two events happen nearly simultaneously. So either one can happen first. In other words, this one can update and this one then read, or vice versa. And so the outcome will be non-deterministic. And this is one of the sources of difficulties of distributed shared memory. Okay? So there are various consistency models. I'll let you read these consistency models because I've already spent a lot of time. And the idea is that sequential consistency, which is the most strict form of consistency, has a non-trivial performance overhead. Therefore, in order to avoid that performance overhead of sequential consistency, we define less strict consistency schemes that improve the performance, but they create dangers of things happening out of order. And if we don't want that to happen, we can always use synchronization. Whenever we want two events to happen exactly the way we want them to happen, you can synchronize the processors, and then all the events after the synchronization point occur after all the events before the synchronization. Okay, so these are various forms of consistency. The final topic is that of transactional memory. This is one of the ways that we can use a design of memory, hardware memory, and sometimes it's implemented in software, but ideally it should be in hardware to be very efficient. A transactional memory guarantees that all the operations in a transaction occur in atomic fashion. So for example, this is a bank transaction. Transfer X dollar from account A to account B. Okay, if the balance of account A is greater than X, then reduce that balance by X, else return insufficient funds. Then add that X to the balance of account B, then return transfer successful. Okay, now if these are basically instructions or statements that happen sequentially, there's a chance that A is updated while B is not updated. And then if some other processor is not yet updated, okay, because it occurs later, some other processor that accesses A and B may get an inconsistent picture where A has already been reduced and B has its own value. So the transfer from the point of view of that other processor has not been done. This account has less money now, but this account does not yet have more money as a result of the transfer. However, if we guarantee in some way that the values of A and B do not become externally observable to other processes or processors until all three of these operations have been completed, then we don't run into that problem. Because the old values of A and B will be available to other processors. Those are consistent values. And then only after all three of these steps have been executed, A has been updated and B has been updated, that other processors can see the new values of A and B. So this is a simple example that shows the importance of consistency. And if we can design the memory to support this kind of thing so that we sort of bundle together a bunch of instructions or statements and say, okay, execute all of these before you change anything in memory, then a lot of the headaches that I mentioned earlier will disappear. Okay, so let me stop at this point. This is the end of lecture 6. Please take care, stay healthy, and I will see you in lecture number 7, which is part 2 double prime in the textbook.